In the last video, we proved a theorem, at least half of the theorem, that says that there's a one-to-one correspondence between these triples, so these right triangles that have area n and sides ABC, and points that have both rational coordinates, positive rational coordinates on the elliptic curve y squared equals x cubed minus n squared x. And I want to use this actually today to show something, to come up with a triangle that you maybe probably would have never thought about. So I want to ask a question. Okay, so we'll start with a question. Is there another right triangle with rational sides and area 6 other than 3, 4, 5. Right? The 3, 4, 5 is the obvious right triangle that has area 6. Is there another one? Another one that has area 6 and it's also right and it also has rational sides. This is not an easy question to answer, just like off the top of your head. Because, obviously if you change one side, you also have to change the other ones. If you increase this leg, you have to decrease that leg to keep the area being 6. Definitely integers are not going to work anymore. So probably going to be some rationals if it's even possible. Okay, so we'll try to answer that question. So first of all, so that means we're starting with that triangle. So that triangle has sides, let's say 3, 4, 5. These are the two legs, and this is the hypotenuse, right? So these are positive integers. Surely 3 squared plus 4 squared is equal to 5 squared, and 1/2, 3 times 4 is equal to 6, right? So my n here is 6. So n is 6. So what I'm going to do first, so this belongs to S. What I'm going to do first is to find the corresponding point on this elliptic curve. So the elliptic curve now in question, right, n is 6. So the elliptic curve in question here is y squared equals x cubed minus 36x. So I would like a rational point on this curve that has both positive coordinates. So what do? Well, I use these formulas here. So what do we have? So that would be x would be n is 6, a plus c, so let's say a would be 3, let's just make a 3, and b is 4. So a plus c, so that's 8, so 3 plus 5, divided by 4. And y is equal to 2 times 36, right? That's 6 squared. Still a plus c, so 3 plus 5, and divided by 16 this time. So what do we get? This is 8. 8 divided by 4 is 2, so that's just 12. That's my x. And here, so this is 8, right? This is 16, and this is, so 2 times 8 is 16, divided by 16 is just 1, so it's 36. So I get the point P equal 1236, and this belongs to T. This is a point that lies on the elliptic curve x cubed minus 36x. Okay, I encourage you to sketch this elliptic curve and actually find this point on it. All right, so that's the one-to-one correspondence, right? We knew that we can get a point on this elliptic curve. But there's an advantage of having a point on an elliptic curve, a rational point. Namely, I can find another rational point on an elliptic curve if I have one. How? Well, you know it by now. I can try to double that point. I can try to compute 2p. So let's compute 2p. I already know, well, all right, let's compute 2p. I already know that the coordinates of 2p will be rational. I just don't know that they're going to be both positive. So just to remind you, right, if you have an elliptic curve of this form, y squared equals x cubed plus ax squared plus bx plus c. And you take a point, P, with coordinates x, p, y, p. How do you compute 2p? Well, 2p is the slope of the tangent line, lambda squared, minus a minus 2xp. So if I call all this x2p, then the y coordinate is minus lambda x2p minus yp plus lambda xp. I just want to turn your attention to the fact that in that other video there's a mistake. There's a minus here, but it should be a plus. This here should be a plus, right? There's no mistake in computing p plus q, but there's a mistake when I was computing 2p and I had a minus. There should be a plus. So what is that lambda? Lambda is the slope of the tangent line, and the slope of the tangent line is equal to 3xp squared plus 2axp plus b over 2yp. All right, looks like lots of computations, but hopefully not too hard, and hopefully the benefit will be interesting. So let's do this. So we need to compute some of these values. So let's first identify these a, b, and c. So these are not the same a, b, and c as here, right? I'm just to be sure, right? This is not the same as that. These are the coefficients here. So what's a? Where's my curve? Here's my curve. A is the coefficient at x squared. There is no coefficient at x squared, so a is 0. B is minus 36. And c is 0. Okay, well that should make some of the formulas a little easier. So now let's compute lambda, because we're going to need that. So lambda is 3xp squared. So here's my xp, right? This is the xp. It's called xp. And this is the yp. So this is 3xp squared. So it's 3 times 12 squared. A is 0, so I don't have to worry about that. And b is minus 36, so it's minus 36. Divided by 2yp, so it's 2 times 36. Let's see if we can simplify this. It looks like number 12 plays a big role here in all this. So it's 3 times 12 squared, right? Minus 36 is 3 times 12. And 36 is, as we said, 3 times 12. So I can cancel 3 times 12, right, in the numerator and denominator. So cancel this and that, so 12 remains. This becomes a 1. And 3 times 12 here also goes away. So what do we get altogether? We get 12 from this term minus 1, so 11 over 2. Okay, so lambda is 11 over 2. It's not too bad. So now let's compute the 2p, and let's compute 2p. So first x2p. Can't decide on the color. x2p. So it's lambda squared, so that's 11 halves squared, so it's 121 over 4. Lambda squared. A is 0, remember, so there's no a. And minus 2xp, and xp is 12, so minus 24. Let's see what this is. This doesn't look too difficult, so it's 121. Let's get a common denominator of 4. So I get 96 over 4. 121 minus 96, that looks like 25, actually not a bad number. I don't know if there are any bad numbers, but 25 over 4 it looks good. And then let's compute y2p. So this is, according to this formula, minus lambda, so minus 11 over 2, times x2p, so 25 over 4, minus yp, yp is 36, plus lambda times xp times 12. Okay, so let's do some calculation here. What we get, common denominator 8, minus 11 times 25, that's minus 275. 36 times 8, minus 36 times 8. And finally plus 4 times 11 times 12. Okay, I'm not going to do this in my head. I have it computed here. It's minus 35 in the numerator. So these are the coordinates of 2p. So 25 over 4 and minus 35 over 8. That's a bummer because y didn't come out to be positive. X is positive though. That's actually good because y not being positive is not a problem. Because every elliptic curve, let's suppose I have a graph like that. Every elliptic curve, if we find a point here which has a negative y coordinate, so let's say x0, y0, then above it we have a point x0 minus y0. And you see this point also has rational coordinates, right? If this one has rational coordinates and has y0 being negative, then there is another point that has exactly the same x-coordinate and a positive y-coordinate, namely the negative of that negative. So yes, this point lies on the elliptic curve, but also the point 25 over 4, 35 over 8 does as well. So I can now erase this calculation. So I can say that 2p is equal to 25 over 4 minus 35 over 8. It lies on the curve, lies on y squared equals x cubed minus 36x. So also, remember, if you negate the y coordinate, you actually get negative minus 2p, which is has just the same x coordinate, but the negative of the y coordinate lies on y squared equals x cubed minus 36x. Okay, but minus 2p not only has rational coordinates and lies on this curve, these are both positive. So that minus 2p, that point is actually in t. So what? Okay, so what we took was, we took this congruent number 6, we took a right triangle 3, 4, 5, the most famous right triangle probably there is. From this we got a point on the elliptic curve y squared equals x cubed minus 36x. The point was 1236. What we did, we doubled that point sort of blindly. We got that point. We didn't like it very much, but we know that the negative of it actually has both coordinates being positive and rational. So that is a point here in t. So what's the big deal? Well, because I can now, if I have a point in t, I can now apply this transformation to get in another triangle. Okay, it's a one-to-one correspondence between s and t. So I know I'm not going to get the same one back because that triangle corresponds to the point 1236. So that point which lies in t must correspond to a new triangle. It will be the right triangle and the area will be 6. Now that should be exciting because, as I said, it's not so easy to find another triangle, right triangle with rational sides that has area 6. But this now should just give it to us. Okay, without doing any complicated calculations. I mean, this wasn't too complicated, I think you agree. I probably had to use a calculator only once here, and if I didn't really want to, I wouldn't have to. And it gives us now, it should give us now a new triangle. So let's see what the triangle is. So I am going to, now that I have this point, I can erase some of these calculations. And I will not need this anymore. So let's compute the A, B, and C. So A is equal to, all right, so it's X. So this is now my X, right? This is now my X. And this is now my Y. So it's X squared. Oh, that's complicated kind of. 620, what's 25 squared? Yeah, 625. Divided by, 625 divided by 16. That's just X squared. 625 divided by 16. Minus, well, N is 6, so minus 36. Divided by Y, and Y is 35 over 8. Okay, again, I've done this calculation before and it comes out to be 7/10. Not too bad, okay? 7/10, 0.7. All right, B, now B. What is B? It's 2nx, so it's 2 times n is 6, and x is 25 over 4. And I'm dividing it by y, by 35 over 8. And what you get from this is 120 over 7. Finally, C. So what do I going to do? C. Maybe erase this. So C is x squared, so again 625 over 16 minus 36, sorry, plus 36 over 35 over 8. So what this gives me is 1201 divided by 70. Wow, this is a new triangle. It's a right triangle. I'll have to check this. I mean, I don't have to because the theory works, but like I like to check things. So you see one side is really short, it's less than 1. 7/10. The other side, well, that's like more than 10. It's like almost 20. It's like really, 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 really long. Okay? 120 over 7. And here comes the hypotenuse. 121 over 70. All right, first the area. What do I get? It's one leg times the other leg divided by 2. That's 6. That's victory, right? We wanted to get 6. How do I know it's a right triangle? How do I know this angle is right? I can just check by the Pythagorean theorem. So 7 over 10 squared plus 120 over 7 squared. All right, I'm not going to do this. Check. You can just use a calculator. That's the same as that. So this is another